I guess people will, but we should also wait for the chair to decide. Let's see what Shanmugapriya said.
Yeah. Hi, Subrat.
Hi, Panos. How are you?
Good, good. Hi, Spenta.
Hi, hi. Hello, Panos. How are you?
Good, good.
Yeah. Nice to see you after a very long time. Yeah.
Yeah, yeah. Also, I hope that I will see you at Crete at summer.
Yes, yes, yes. You will.
Okay, maybe we can start today's seminar. We're very happy to have Panos Betzios from Ghent University, and he'll be talking to us today about an inflationary cosmology from AdS wormholes. Please go ahead.
Okay, thank you. So first, I'd like to thank the organizers and all of you for giving me the opportunity to speak in this very nice series of seminars. So today I will present some work that was done in collaboration with Olga Papadoulaki, and this gave rise to this publication, but also during the last part of the talk on some, let's say, a bit slightly more recent work with Olga and Ioannis Galamas. So this work will be related to how one can understand some kind of inflationary cosmology and connected with AdS wormholes. So I've prepared quite, because I didn't know who is going to be in the audience, I've prepared a quite, let's say, thorough introduction. Feel free to ask me and stop me at any point. Okay, sorry. So maybe all of you have already seen this well-known plot. So in this figure, basically, we depict the history of our universe. Towards the right-hand side of the plot, it's the current era, the current times. And when we go towards the left, we go back in time. So very good cosmological data show that our universe is currently expanding. It has a non-zero temperature, small but non-zero, and it is extremely uniform at large scales. So in this talk, we'll mostly be interested about the initial, let's say, stages of the evolution of the universe and essentially to physics before the CMB production. So near this left-hand side of this plot. So any theory of the universe should explain some features of the cosmic evolution according to experimental data. So it should explain why the universe appears to be nearly flat, homogeneous, and isotropic. It should explain why causally disconnected regions of space-time look very similar. Also, we don't observe any exotic relics such as monopoles around us. And also, it should be a theory that produces primordial perturbations that are nearly scale invariant. And here I give you a well-known formula for the curvature perturbations that is parameterized in terms of the spectral index NS. And okay, there are various, let's say, data that show that this is NS is close to 1. And okay, there have been some more recent data from the Atacama telescope that actually slightly shifted, let's say, this the well-known value for NS. Now, okay, it's not yet clear which one in the future will remain, but it's sort of in this regime, this ballpark between 0.965 and 0.97. Now, inflationary theory is actually a theory that incorporates all these features, and it is quite successful. So in this theory, basically, one takes the cosmological constant and promotes it to a potential that depends on the field phi. And now this field phi could be either a new particle, the inflaton, or in the last part of the talk, I will also discuss some potential case where the inflaton could be even the Higgs boson. Now, there are various models that are consistent with all these features that we discussed. They also explain additional observational features, such as the tensor to scalar ratio that I depict in the figure here. And you see here various inflationary models that fall very well within, let's say, the experimental constraints. But it is also fair to say that it is actually quite hard to embed inflation in some kind of UV complete model, such as string theory or AdS, and that typically is because they later prefer vacua with a negative cosmological constant and not with positive cosmological constant. Okay, so let us now go towards our main questions in this talk. So the questions that we would like to understand a bit better is basically what gave rise to the initial conditions or state of inflation. Because, even if we accept the inflationary theory, typically one puts some initial conditions, one has some kind of potential and introduces the scalar field, assumes that the scalar field started high up in the potential and then had some kind of slow evolution. Now, also, even within the context of inflationary theory, if we trace back the evolution laws back in time, basically we still have some kind of initial singularity, or the universe becomes really small, it reaches Planck scale, and our physical laws cease to work. And one might argue that, if you want to really understand this regime, you need a complete theory of quantum gravity to really understand these problems. But as physicists, it is also natural to ponder and ask whether there is at least some approximate way to at least compute or estimate probabilities for certain events in this very early universe cosmology. Now, Hartle-Hawking gave one such appealing proposal for computing the wave function, what they call the wave function of the universe, and this is based on the so-called Wheeler-DeWitt equation and approach. Now, in this approach, one basically uses the canonical or Hamiltonian formalism of general relativity and promotes the constraints that express diffeomorphism invariance, that is the symmetry of GR, to quantum operators that annihilate the wave function. Let me now give you a very brief review. I hope, maybe it's very introductory for you, but even for the students. So let's imagine we have, let's say, some four-dimensional metric, and then let us decompose this metric into some time direction. I will denote this with T, and also some space direction. I will denote this with Xi. And then a general decomposition of the metric involves two functions, n, that is called, four such functions. One of them is called the lapse function, it's this n, and three functions are this shift, the components of this shift vector. And with Gij, we will denote the spatial metric on a slash sigma. And basically, this form of the metric tells you that you have some kind of foliation of the four-dimensional spacetime. And then this n and I basically capture for you how you change as you evolve from slice to slice. Now, let us start again with some Einstein-Hilbert matter action that I write down here. And then when you go to this ADM parameterization, you can define some sort of Hamiltonian that is conjugate to this time t. And then this can be written in this form. And now this Hamiltonian, of course, depends on the three metric Gij, on momenta that are conjugate to these three metrics. And also, if you have some kind of matter, it also can depend on some additional matter contributions. Now, we said that our theory was diffeomorphism invariant. So the manifestation in this Hamiltonian formalism is basically that these choices of n and I were arbitrary, and basically any physical state or configuration should be independent of this choice of lapse and shift, because basically you can perform coordinate reparameterizations. Now, according to the Dirac quantization, this leads to constraints. One of them is the Hamiltonian constraint, and the other is the momentum constraint. And in our case, let us also consider a matter scalar field phi that for us will play the role of the inflaton. Now, at the quantum level, one has to impose these constraints that act as operators on the wave functions and should annihilate the wave function, as I depict here. Now, the trouble with this approach is that actually it is not really well defined. These functional differential equations never really took a very well defined meaning. But at least, fortunately, there exists some kind of unsaturated or truncation that is called mini superspace unsaturated or truncation that is better defined, and this typically leads to ODEs or PDEs in this case. And fortunately, as we argued, our universe to a good extent is isotropic and homogeneous, so this unsaturated is also physically relevant for our purposes, as I will soon describe. Now, the Wheeler-DeWitt equation in this no-boundary proposal takes... Yes, question. Okay. Okay. Is it no question? Okay. So I write down here the form of the Wheeler-DeWitt equation in this mini superspace and such. And basically, in this case, one can show that the momentum constraints are satisfied automatically, and one actually has to solve only one constraint, the Hamiltonian constraint, that is also called the Wheeler-DeWitt equation. Now, even with this vast simplification, still one has to supplement this equation with boundary conditions. And there are two main, let's say, boundary conditions in the literature. One is the Hartle-Hawking no-boundary proposal. And as I will explain in the next slide, in this proposal, basically, it is assumed that as we go back in time, we have to make an excursion to Euclidean signature and consider geometries that are compact and close off smoothly at early times. And then, as I will also show, the resulting state or wave function corresponds to the Bunch-Davies or Euclidean vacuum, which is sort of the analog of the Minkowski vacuum. We have some, let's say, positive cosmological constant. Now, there is also an alternative proposal that is called the tunneling proposal by Linton and Vilenkin. It is slightly more complicated for me to describe this here. You have to define some kind of probability flux, influx, outflux in the superspace, in the space of third geometries. And we will contrast these two these two boundary conditions in a slightly more concrete example. Now, let us take the simplest example, just empty de Sitter, just fixed positive cosmological constant. And in this case, the Hartle-Hawking proposal basically describes a complex metric. So how do you form this complex metric? You take the Euclidean de Sitter, that is an S4, a four sphere, you slice it in half, and then you glue to it half of the Lorentzian de Sitter, that is the hyperboloid, right? And then basically you make a figure like this one on this right-hand side. And here I also write for you the metric of the four sphere and the metric of de Sitter, and basically also the contour that you need to take in the field space. So this is, let's say, a classical version of what the no-boundary proposal means. Let us now do some kind of semi-classical description by basically solving the Wheeler-DeWitt equation with positive cosmological constant, no matter, and also employing a WKB and such, where we send this kappa that is 8 pi gh bar to 0. So you have a time-independent Schrödinger equation, and then you can solve this in a WKB method. And now this WKB method basically involves an ansatz of this type, either this type on the left-hand side or this type on this right-hand side. Now, from the form of the potential, you see that the potential starts being positive, like a harmonic oscillator for small a, and then it goes to minus infinity for very large a. A for us is the scale factor, the size, let's say, of the three sphere. And you see that zero energy conditions, zero energy solutions, basically you see that this equation is an eigenfunction with zero energy. You find that basically for large a, the wave function is naturally oscillatory, while for small a, the wave function can be either increasing or decreasing. Now, the two choices, the no-boundary or the tunneling proposal, basically are related to the two choices in this Euclidean or small a region. So in the tunneling proposal, basically one picks the decreasing solution, while in the no-boundary proposal, basically one picks the increasing solution. And then one has to do a WKB matching procedure with a Lorentzian solution for large array, and then one finds the full solution for all values of a, both small and big. Now, for large a, the solution is oscillatory, so it's naturally Lorentzian. You see, you have this kind of oscillating behavior, while for small a, you see that you have either an increasing function or a decreasing function, and this also tells you that the wave function has a more natural Euclidean interpretation that is also consistent with this sort of picture that I also drew at the classical level before. So is this clear so far? Okay. So if there is no question, we proceed. So now let us include also the presence of a scalar inflaton field phi and assume also a slow roll approximation where basically both the first derivative and the second derivative of the potential are small. So this is the region here where you basically inflate, and then perhaps you also can have some kind of heating stage of the universe. Now the Wheeler-DeWitt wave function depends on two arguments, on a and phi, And basically what you can do with this Wheeler-DeWitt wave function is you can form, let's say, norm-squares of these wave functions and compute, for example, ratios for different histories or realizations of the inflating universe, as I write down here. Now, in the context of slow roll inflation, you can again perform a WKB approximation and compute again the Wheeler-DeWitt wave function. I will not give you all the details. You can read these very nice reviews that I mentioned here. So here I write down for you the two main cases, the no boundary and the tunneling wave function. You see that they both have some kind of prefactor that depends on either e to the minus s Euclidean of phi or e to the plus s Euclidean of phi in the tunneling proposal. And this s Euclidean of phi basically is the on-cell action of Euclidean de Sitter of the sphere. And then it also has some kind of oscillatory part, and this oscillatory part is basically related to the action in the Lorentzian oscillatory region when the scale factor becomes large. Now, in order to derive basically this, you have to solve these equations in the two regimes, as I said, do this WKB matching, and okay, you have to also choose where exactly you make this matching. Typically, this is performed at the first horizon crossing, as people say in the inflation, near the beginning of inflation. So if you want to see more details, you can read these reviews that I mentioned here. But basically, this is
R-Gothic in first formula, R-Gothic.
What is the logic in the
R-Gothic. Letter, this first formula, R of exponent. What is R? Yes.
This is the real part. Yeah, it's like a cosine. Yes, sorry. So in the no boundary proposal, because it's CPT invariant, basically it's like taking a wave and it's conjugate, so you find the cosine. So it's a real wave function. So this R is basically the real part. That's what I mean by this R. Okay, thanks. So that was the leading piece, but okay, it's actually possible to go even beyond mini superspace as long as you consider small fluctuations. Now, if you consider homogeneous fluctuations, basically you can make a good computation that was done by Hartle and Hawking, and you can show that the no boundary proposal basically predicts a correct spectrum of primordial perturbations with a Gaussian suppression factor. So for every mode that you have, let's say in your scalar field or in other fields, basically you find this Gaussian suppression factor. So this tells you basically that it describes the cosmological analog of the vacuum, like in a harmonic oscillator. Now, in the tunneling proposal, if you remember, this minus sign was a plus sign, and this has a grave result, and this result is basically that such fluctuations have become unsuppressed. Now, people have tried to argue that you can sort of save this, but okay, at face value, this is a problem with the tunneling proposal. Okay. Now, let me also mention something else. So if we assume a slow roll inflationary scenario, we can split the evolution of a field into UV modes and infrared modes with respect to the Hubble scale H. And then we find one, as was argued by Starobinsky in the 70s, basically the infrared physics at large time scales and large lengths are basically governed by some effective stochastic equation. So in this stochastic equation, basically you have some kind of random forcing, that is this function psi of tau, that is also like a white noise. And also this is supplemented by a Fokker-Planck equation for the probability that the field has a certain value at a certain time, that I write down here. Actually, Starobinsky in his work actually also showed that for a potential that is bounded from below, one finds an equilibrium distribution that is consistent with a no boundary proposal. So the equilibrium solution of this stochastic, let's say, formalism is actually the same as the one predicted by the no boundary proposal. So this is also another, let's say, a good feature of the no boundary proposal. Now, I mentioned the good things about the no boundary proposal, but now I will mention a sort of problem with the no boundary proposal that is a sort of exponential hierarchy type of problem. So I guess you all are familiar with the current cosmological constant that basically tells you that the current cosmological constant is extremely tiny with respect to Planck units. So this is now, but with the no boundary proposal, there is actually an exponentially worse problem. So the non-boundary proposal, if you remember, this probability depends on e to the minus s Euclidean of de Sitter, and basically since the on-cell action of the Euclidean de Sitter is negative, you find a positive exponential, a positive number in the exponential. Now, if you form ratios with this type of weighting or measure, you find that there is an overwhelming probability or a huge ratio that basically your universe will be empty and cold with the smallest allowed number of inflationary periods. So basically your universe prefers to nucleate here directly, and it is actually exponentially suppressed. The probability actually to start your universe high up in the inflaton potential is really exponentially suppressed. So basically, this tells you that in the space of all possibilities and histories of the universe, inflation is an extremely improbable event. So that's the interpretation of this fact. So is this problem clear? Okay.
Panos, can I ask a quick question?
Yes.
In the previous slide, I think you mentioned something about chaotic inflation. Yeah. Can you explain again why we need a bounded, the potential to be bounded above?
Oh,
below?
because you see, there is this notion of sign. So I think if it becomes negative, you cannot really trust this formula. This minus, you will pick an additional minus. So this is something like an absolute if you want to be a bit more careful. There is some issue here with change signs, but I think people have studied this also. But okay, I just mentioned the original work of Starobinsky here.
Okay, thank you.
Okay. So ideas to evade this problem. We said the tunneling wave function. This evades this issue, of course, because it weights with the opposite sign. So basically, this plus will become a minus here. But then, as we said, you have a problem with perturbations. You have to make some other assumptions that Linde and Vilenkin made, but it is also not clear whether these assumptions are okay or not. Now, other authors assume that you can make some selection rule or anthropic reasoning, which is the standard, solution of hierarchy problems. But okay, it's not very scientific, at least according to my perspective. Another issue that we should always keep in mind is that the gravitational path integral is not really well defined, right? It's a non-normalizable, renormalizable theory, and we also have this conformal mode problem. If you know the Euclidean action is unbounded from below, so really you have to understand it in the complexified field space. Maybe you have to pick some appropriate complex contour. You have to do all this Picard left edge theory, but this is really, people are working on this. It's very interesting, but it's really, really hard to make this precise when gravity is involved in the game and not just a simple, quantum mechanical system. Now, another possibility could be that there are some strong quantum effects coming from loops, maybe secular terms in expanding cosmologies, and this actually have a very important non-perturbative effect on the wave function, and then this becomes very different than your naive, let's say, WKB expectations. This can be realized in some two-dimensional models, but yeah, as far as I know, nobody has really made anything concrete with that in higher dimensions. And okay, in this work, in this talk, I will try to change somehow the assumptions of setup that gives us our cosmology. So that's, let's say, the road that I will follow from now on.
Sorry, I have a question here.
Yes.
Yeah. Sorry, the question is, you initially said that when you're motivating the proposal that you're looking for solutions to Wheeler-DeWitt. But after that, but no boundary is kind of logically different, right? It's saying it's a particular prescription for generating solutions to Wheeler-DeWitt. The reason I'm asking this is that, we could just say we have the following solution to Wheeler-DeWitt, which, has the correct sign for fluctuations because you want that for normalizability. Yes. But maybe we don't take seriously the zero mode prediction from no boundary. I mean, if you're just looking for solutions to Wheeler-DeWitt, there is a claim that this is somehow forced. One of these two choices, plus or minus, is forced on us by Wheeler-DeWitt, or are these like separate issues?
Yeah, I think, I think this involves, in some sense, rotating in a different way the zero mode, right? In the complexified, choosing a different contour in the complexified field space for the zero mode. That's basically what you're saying.
Yeah. So I was saying, let's say I don't try to get my solution by doing a no boundary path integral. I just look at my solution and I ask, does it satisfy Wheeler-DeWitt equation?
Yes.
So then for the I think what you're calling the UV modes or the fluctuations, the non-zero modes, yes. You will get some spectrum which is forced on you by Wheeler-DeWitt. Like it's not it's that structure is forced on you by Wheeler-DeWitt. And
plus
then-
normal stability, as you said, which gives you an equivalent result as the no boundary. That's
right. But for the zero, is the sign of that fluctuation necessarily linked also to the sign of the behavior of the zero mode, or are these like independent issues just from the perspective of Wheeler-DeWitt, not from perspective of doing the path integral?
I guess in the Gaussian level, you can sort of decouple because you can basically split the modes, right, in pieces. So if you work in the quadratic Gaussian level, I think you could do what you say. Now, I'm not sure if you are in the nonlinear regime. So if you, beyond that, whether you can decouple these two things.
But then I could just say the wave function is given by taking the Vilenkin prediction for the zero mode and taking the Hartle-Hawking prediction for the non-zero modes. And that is the wave function of the universe. I don't care how I got it. Like, that's my answer. Like, what would be wrong with that?
For the Gaussian level, I think that's fine. And I think people have proposed something like this. I think there are papers. But if you are fully nonlinear, I'm not sure how,
But is there a clear problem if you're fully nonlinear? I mean, does nonlinearity lead to a clear problem?
I'm not sure. But it's just that I see that modes start getting coupled. So I'm not
Okay.
sure that you can really solve it in this way.
Okay.
I'm just giving you a very quick answer. I haven't really
Okay.
thought it very carefully.
Okay, thank you.
Yeah. Okay. Okay. So now let us change slightly gears and go to a context where basically this no-boundary proposal works perfectly well. And this is the AdS CFT correspondence, where basically we have a negative cosmological constant. So here, for example, I draw for you global Euclidean AdS4, and then basically on its boundary, that is an S3, basically there is a dual CFT that we can think of intuitively as living there. And basically one can also show that in many cases, one can show that computations on both sides agree. So the quantum gravity on path integral on AdS is the same as the, let's say, partition function of some dual CFT. And if you have supersymmetry, you can even compute things even at finite n, for example, in ABT again, in 3 dimensions. Now, here in this case, the reason why the no-boundary proposal works and this minus sign is correct is basically the fact that the on-cell action of AdS after you perform holographic renormalization is properly positive. So there's no problem as before where the on-cell action of the sitter was negative. So you start with something that is positive, and then you expand in fluctuations, and everything you find it to be properly Gaussianly suppressed in the vacuum, etc., etc. Unfortunately, as you know, this setup does not have any direct relation to inflationary cosmology, right? With a simple, at least, analytic continuation, maybe with some more complicated ways you could relate it. And these complicated ways are the context of this next slide. So there have been people that were trying to basically use a sort of AdS ideology to understand, let's say, the sitter. For example, in this work by Hartle-Hawking Hertog and Maldacena Turiazi-Young, basically they try to study a different contour. So here with this blue and green line, I show for you the usual no boundary, let's say, proposal and Hartle-Hawking contour. And here with these red and yellow lines, I show you a sort of different contour that has the same initial and final points, but this contour passes basically through minus AdS4 geometry. Of course, now this opens a new can of worms, because one might argue, is there contour independence in the field space? Can you really change contours that freely? Which of the two is the steepest descent contour? And then, you basically land again to the complexity of Picard left sets, which you should understand really, really well. Now, there has been also another approach. You could try to do this domain wall cosmology correspondence by Skinters and Townsend and other collaborators. But there you have to do some multiple analytic continuations to relate basically the sitter with AdS. Again, it's not really very clear, at least to my opinion, a clear analytic continuation as the simple tau goes to IT. Now, there has been a context where basically you can relate with the
Sorry, Panos, I missed something. Could you please repeat something? At some point you said in AdS, the minus sign is the correct thing. Could you please explain that again? Sorry.
Yes,
Yeah.
yes.
Yeah.
So the reason why the minus sign is correct is basically that the Euclidean axion of AdS is positive after you do holographic renormalization. So you find something that is less than 1. E to the minus s is properly, less than 1. And then you can expand this s, to higher orders, and then you find something like minus delta phi operator delta phi, blah, 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 right? And then
is there an analog of the zero mode problem for AdS? What does the zero mode even mean in the case of AdS?
I don't see an analog of that problem. No. Yeah.
Sorry, the reason I was asking this was this isn't it, maybe I said I'm just misunderstanding something, but the zero mode problem you just mentioned, it's relevant in the case of slow roll inflation, right?
That's right.
Would it be relevant if you just had de Sitter?
Yeah, that's right. Yes.
But if you just had de Sitter,
well, if it's pure de Sitter, basically you're saying here the potential to be just a constant, right?
Yeah, exactly. If it's pure de Sitter, then I think we don't have
then
de Sitter.
Basically you don't have options, right? Wherever you are, there is some, there is some translation invariance in phi.
Right, exactly. Right, that's right. So in AdS, are you really seeing a solution to this problem? Because you're really thinking of the case where you're purely asymptotically AdS, right?
I see. Okay, here I mentioned pure AdS, but imagine you have some kind of model where you have again some potential where the minimum is at 0, at 0 is negative, and then it's a bit slightly non-trivial.
I see. But this example you're mentioning right now is really the case where you're asymptotically pure AdS, right? You don't have some approximate notion of AdS. So I completely agree this is the correct answer for AdS is the ZCFT, but I'm just wondering if it's directly relevant to the zero mode issue you just described.
It's not directly relevant to the previous zero mode issue a priori. Up to this point that I'm discussing, the thing is not related. I'm just saying that in AdS, the analog of the no-boundary prescription makes well. And also if you have some potential that is non-trivial, maybe it's it has some negative minimum, maybe it's slightly non-trivial. You can have RG flows, right? And then you understand them very well also.
Yeah. Okay. Thank you. Yeah.
After this small digression, yes, let's go back to cosmologies in AdS. So there is a context where basically you can relate somehow some kind of cosmology to AdS physics. And this is basically through Euclidean geometries that have some Z2 reflection symmetry, because then you can slice them in half and define basically states or wave function for a Lorentzian evolution upon analytic continuation. So you need a Z2 symmetric solution to do that. And a simple such Z2 symmetric solution is a Euclidean wormhole, basically like the one that I draw here with two Euclidean AdS boundaries. And these geometries, as I depict here, you can slice them here. In fact, you in half, and then you can analytically continue tau to IT, and then you find some kind of Lorentzian geometry. Now, for Euclidean AdS wormholes, as the ones that I depict for you here, where basically the scale factor has a minimum, so the geometry is large and then it has a minimum in the middle. Basically, under this analytic continuation, you find that the corresponding cosmological spacetime in real time is basically a Bank-Crunch type of cosmology. And this you can show easily because this say double prime less than 0. When you do this analytic continuation, basically becomes a dot less than 0, right? So the geometry likes to crunch. So that's interesting, that's nice. But as we said, most of these wormholes, upon analytic continuation, the Lorentzian manifold crunches and does not allow for any period of inflation. So our idea in our work was the following, was maybe it is possible to combine basic features of both anti-de Sitter and de Sitter. So this would mean, actually, that one needs some Euclidean wormhole that is asymptotical Euclidean AdS, and then when you go towards the throat, basically it becomes something like Euclidean de Sitter, or like the sphere. And here I have some impressionistic version of options. On the left hand, you see the no-boundary proposal. On the right hand, you see this typical Euclidean AdS wormholes. And here in the middle, I saw something that is in between. It starts from Euclidean AdS, the geometry strings, but then it expands near the throat slightly, such that upon analytic continuation, you can sort of glue to it an expanding universe. So let me I hope this, at least impressionistic cartoon version is clear. So let me become slightly more explicit in that. We call this, well, half of this geometry is wine glass, half wormholes. So people had discussed in the past some asymptotically flat similar solutions, but we're interested in the asymptotical AdS case. And in their defining properties is that basically the geometry becomes a Euclidean AdS space on each of the two boundaries. And then in addition, the scale factor should exhibit a local maximum in the middle. And as we mentioned, these are good initial conditions for a subsequent inflationary evolution. Now, of course, it is not possible to support the solutions for any potential, right? Because in some region it looks a bit like AdS, in some region it looks a bit like the CTEP, the geometry. So basically you need the scalar potential that takes both positive and negative values. And here I give for you two examples that we studied in our works. So the potential could be something like this, or the potential it could be something like this on this right-hand side. And now in the next slides, I will give you an explicit model with Lagrangian dynamics that basically realizes this sort of solutions that I motivated here. So is it at least clear what our motivation is for these solutions? Okay. So let us now consider a general model of general relativity, an inflaton that we will denote with phi, and then perhaps you can add some kind of radiation or matter Lagrangian. And let us also focus in some spherical, symmetric, and homogeneous ansatz so that we are able to sort of solve the equations of motion. Now, there are three types of equations. There are equations, let's say, for radiation and matter. I will treat them in this talk as being like a fluid. Of course, we have some solutions that are with explicit, let's say, I don't know, U1 gauge fields or SU2 gauge fields. But for the purpose of this talk, I will just treat this radiation and matter in a fluid approximation for simplicity. And then, okay, the rest of the equations are basically the Einstein equations and the inflaton equations. So the Einstein equation is basically reduced to this constraint, and this is the inflaton equation. Now, in our work, we found that these wormholes can be supported either by axions or some magnetic type of radiation. And why this is so? This is because magnetic radiation, basically in Euclidean, because we are in Euclidean signature, these fluxes lead to rho radiation negative. Because the Euclidean stress energy tensor is not like in Lorentzian, it's E squared minus B squared. So if you have a dominant magnetic component, this T tau tau is basically negative. And you see from this equation, this rho radiation will acquire a plus sign effectively because rho radiation is negative. Now, why this sign is important for wormholes? Well, intuitively, you can sort of understand it. The geometry likes to shrink, but then you need some kind of flux that allows basically this solution to exist and support the throat from really collapsing. So here I give you the dynamics for these wormhole solutions. So gravity, basically incorporated by this term minus A over A squared in this equation, likes to shrink the scale factor, right? This is a Euclidean version of the gravitational focusing. So if it's just pure gravity, basically you cannot really re-expand. On the other hand, if you have fluxes, the fluxes actually push the geometry towards expanding, basically from these terms. And at the same time, you have some kind of equation for the scalar field. And this equation basically describes a particle that moves in the inverted potential. So in Euclidean signature, basically you go from V to minus V. And then you also have some kind of friction or anti-friction term, basically due to this A prime over A. And here in these figures, basically give you the full Euclidean evolution, both of the scale factor, the scalar field, and the potential. And the dynamics is the following. So when the manifold is large, basically when A is large, this term is dominating over these terms, right? So this is the Euclidean AdS regime. The manifold is large. Gravity likes to make the geometry smaller. You find that A prime is less than 0, so it shrinks. You have anti-friction in the scalar equation. So you are in this, let's say, inverted potential. So you are in this region where you have anti-friction. This anti-friction helps you to, the scalar particle basically, to overcome this obstacle, this hill. And then at some point, the size of the manifold becomes small. So basically these terms dominate And then basically because they dominate, you find friction, so the manifold re-expands, A prime becomes positive, and then the scalar particle now rolls down, it has some friction, and then it stops somewhere near the minimum of the inverted potential. And for us, as you can imagine, it is desirable to stop near the minimum of the inverted potential because it is the maximum of the original potential. So is the dynamics clear? Please do ask questions here because that's kind of an important part to understand these dynamics.
So, sorry, I didn't understand something. At some point, you said something about axions or radiation, but when you write down the equations of motion, there is a stress tensor on the right-hand side?
Yes, the stress tensor, it's from this term, right? From radiation matter.
I see. And are you looking also at the dynamics of that radiation matter, or that's just given that you're just assuming that that's something which is present?
So we have some solutions that are where we solve these equations explicitly, let's say for some non-abelian or Yuan gauge fields. But okay, here we want to be more generic, right? Because you can have, various fields that contribute to rho. We just treat it in a fluid approximation.
I see. Okay. Thank you.
But okay, I hope at least the dynamics is clear. When you shrink, you have anti-friction, and then when you expand, you have friction, and basically this is what allows you to sort of have these solutions. Now, as we said, basically this classical trajectory, the Euclidean classical trajectory, basically brought us from this Euclidean AdS vacuum, basically high up, this potential, and then if the potential admits some kind of slow roll region, basically we start with good initial conditions for inflation, and then we can also inflate, and maybe we can also have some reheating stage. Of course, so far we were bottom up, so because we are bottom up, we can accommodate various options that are consistent with experimental constraints of inflation, because basically we can choose the slope of the potential here, and we can make such a bottom-up model to work. And then we will also soon discuss a slightly more constrained model of Higgs inflation that is slightly more constrained than this very generic case that I described here. Now, you remember we had some kind of issue in the no-boundary proposal, an important issue that this probability was not well defined, it was bigger than 1. And here we can again compute it basically through this Euclidean on-cell action. And okay, to compute this Euclidean on-cell action, you need to add the Gibbons-Hawking term, also some counter terms to perform holographic normalization. And okay, in general, you do this procedure, and then you can compute this on-cell action either numerically or in some approximations. And then, at least in the cases where we check, this action is basically positive. And it's basically positive because of the AdS asymptotics that dominate the value of the action. So you see that, as we were discussing with Subrat, as in other holographic examples, basically we have a well-defined probability, and the issue of the no-boundary proposal can be evaded. Because basically this action is positive. And as we said, there's a classical trajectory that prefers to bring the universe high up the Lorentzian potential, and the universe prefers to nucleate high up. So these are good initial conditions for the subsequent inflation. Yes, Subrat? I can't hear you.
Oh, so sorry. The question was, what about the fluctuations? Do you get the right scale invariant spectrum?
Very good. Okay, I have a slide in the discussion in the future. We haven't done this computation yet.
Okay.
But okay, let's discuss this at that point.
Okay.
That's an important point. Yes.
I had a question.
Yes.
Like, do you have a CFT picture of what you're trying to do? Is there a...
that's also in the future directions. It could be very interesting to also have a CFT picture. And this basically relies on whether this kind of Euclidean wormholes have some kind of clean embedding in an AdS CFT context. And okay, there are two answers to that, which we will again, let's discuss this more towards, let's say, the future, because that's an important also point.
Okay.
Panos, can I ask another question here?
Yes.
How much does this really explain why the inflaton began high up in the potential? Because don't you have to fine-tune your potential to get the shape in the first place?
Yeah, exactly. So you might argue that in some sense, that's true. If you are bottom up, basically, you see, I got to pick a shape for this potential. So you might say why this like that. You could say, you know, in this previous picture, you would turn this minimum very high. Basically, when you roll down, you might overshoot. That's true. At this point, basically, the fine-tuning of initial conditions comes from a fine-tuning in some sense. Well, you don't really need fine-tuning, but there is some wide regime of possibilities. And then, okay, there are some possibilities that basically allow you to nucleate high up. At this point, that's true.
Okay, thank
I
you.
will soon describe a model where things are slightly more constrained, but yeah, that is indeed true. Okay, so I don't know how much time do I have because I didn't bring it.
You have about 45 minutes. Yeah, you have time.
I have a lot of time. Okay. So now I will try to argue that this idea basically can be embedded in a model that is consistent with experimental data, and it is a simple model that just involves the standard model plus general relativity. So there exists a minimal model for inflation under the name of Higgs inflation. And the idea here is that basically the only particle, scalar particle that we have observed at low energies is basically the Higgs boson. So perhaps this could also play the role of the inflaton. Now, these models of Higgs inflation are described again by an action that contains radiation matter plus, you know, the standard model fields. And then you also have the Higgs field. You have, you know, the usual Einstein-Hilbert term. But you also invoke this sort of non-minimal coupling of the Higgs to the Einstein. And this sometimes is called the Jordan frame action. And okay, one also interesting feature of this model is that you can sort of get the Starobinsky R-squared model in some kind of psi goes to infinity limit of these more general, let's say, models. Now you might say, okay, why did you add this term? It just, you know, came by your head, but such terms actually typically appear where you consider loop corrections to the effective action and are required by renormalization, as was shown in this paper by Coleman, Callan, and Jakir. So these terms generically are generated through quantum corrections and renormalization. And it's the leading term in such a case. Now, the classical analysis of these models is the following. You start with this Jordan frame action, and then you do some kind of while transformation to go back to an Einstein frame. Once you do that, though, you pick this non-canonical kinetic term for the Higgs field, and then you do a filter definition to bring it to a canonical form. And then you find the potential that has two regimes. There is a small field regime where basically the potential is the same as the standard 3-level Higgs potential here for small field values. And then there's a large field value that basically the potential becomes very, very, very different from the usual Higgs potential. And here is a graph of this potential in the chi variables. So you see that for small field values is similar to Higgs. And then for large field values, it becomes this exponential type. And actually, it's really, really smooth with small gradients. And because of that, it can support some slow roll inflation. Now, this model also has been shown to be quite consistent with the CMB. So here I give you some 3-level predictions of this model for 60 e-folds. Some 3-level predictions of this model. And when you choose n star to be 60 e-folds of inflation, basically you find that this model is in a very good agreement with the spectral index and the tensor to scalar ratio that are given by Planck, Bicep, and Keck. So this is a good inflationary model, and also the amplitude of these curvature perturbations basically also constrains this.
Sorry, Panos, I didn't understand something. I thought you just said that you did not compute the spectrum of the fluctuation. So how are you able to what do you mean by amplitude of curvature perturbations?
No. So sorry. So this was for this model, right? The previous one. Now,
okay.
in the context of Higgs inflation.
Oh, sorry, I missed. Oh, sorry, I lost track for some time.
Now I slightly changed the model with this non-minimal coupling.
Oh, I see. Okay, sorry. So now you're just I see.
And you see here there is no negative region in the potential yet.
I see.
We'll introduce this later, but so far, you know, I'm just doing 3-level Higgs inflation. And
Okay,
people have computed fluctuations
Okay,
in
sorry.
level Higgs inflation.
Okay,
And this
sorry.
is basically what I'm read. No, but
Sorry,
it's a good.
I missed it. Yeah, thank you. Yeah.
No, but
thank you.
it's actually very confusing. I should have clarified that. That's a good.
Okay, thanks. Yeah.
Keep in mind. Thank you for that. Okay, so because of that, basically you can constrain this psi star and lambda star basically from this curvature perturbations, and also the value of the potential in the plateau region. So this model now does suffer from some issues. So let us assume that we are at tree level and all the couplings are constants. People have shown that this model basically violates tree-level unitarity at some scale that is given by this ratio. And actually the Hubble scale at inflation is quite close to this ratio. Also, people have estimated what is their heating temperature. It is bounded by these two values. And also they have shown that there are some subtle preheating and reheating processes and issues. Basically because your psi is, to have sufficient inflation, basically your psi cannot be really small, right? So you know lambda, let's say, the Higgs quartic coupling from experiments, and basically this tells you that psi should be relatively large because of this ratio. So basically this leads to some kind of problems with preheating, reheating, and with some violation of this tree-level unitarity. Now, in our context, we'll actually argue that one needs a proper treatment of quantum effects and the UV completion of this model. But once you try to understand quantum effects, you should also keep into mind that there's a caveat in that the scales and the cutoffs are basically background and frame dependent. So it depends a bit in which frame you perform your computations. So let me give you just a small, let's say, idea about what I mean by that. So you see, you have two frames, right? The Jordan frame, the original action, and the Einstein frame. And then you might say, okay, I want to put some kind of scale or cutoff, and then this you can do either in the Jordan frame or in the Einstein frame. And of course, these are non-trivially related to each other with this Weyl transformation. Now, these lead to two different ways of computing quantum effects and quantum completing these models. And we will basically follow this second prescription, which is the standard prescription for loop corrections. I don't know if this slide is very clear. Okay, no question. So once you compute loop corrections, you find that this changes the Higgs potential appreciably. So in the case of no gravity, you find that basically it is very sensitive to what is the value of the Higgs and the top quark mass. So the potential can actually become negative, depending on what is the value of the Higgs and the top quark mass in our scales. So of course, these results are also sensitive to the UV completion because you have to run RG towards higher energy scales. So perhaps if there's supersymmetry, these results could change in principle, but at least it shows that it is possible that once you compute quantum corrections, basically the true vacuum is actually negative and not positive, as in the usual three Higgs potential that I draw with this first line. Okay. Now, experiment. So in the experiment, we seem to be in the critical or metastable regime. So if we assume that we will not find new particles, basically if you run RG to higher energies, you find that basically the central values of the top end of the Higgs particles favor the case where basically the potential will become, the true vacuum will become negative at higher energies. So that's all an experimental fact. So you see that basically this tree-level analysis and this potential that I drew here, based on the tree-level of form of the Higgs potential, was basically incorrect, quite incorrect once you include even these quantum corrections. Okay, so let us now, all this was without any gravitational corrections, but of course we should include also gravity as an EFT, and then we can write down an action in a derivative expansion, more and more derivatives. And then we also couple this to the matter Higgs. You have also higher derivatives. And then you try to compute some RG running of all these couplings. Now, this is very hard, of course, to do for all these couplings. But you can argue that, if you are at large scales, basically your universe is large, you don't really care about these higher derivative corrections. So you can try to focus, let's say, on the lower terms. And basically the lower terms are up to linear in the curvature R. Now, we did this, and you can show basically that the couplings, if you assume that we are in this metastable regime, you can show basically that the couplings do run appreciably when lambda becomes a negative in a certain energy window, as in this scenario. So once you do that, you find an effective Higgs potential, again written in the Einstein frame, that looks like this. Now, this is sort of schematic, and the reason why it's schematic is the fact that we really don't know what happens in very high energies, right? New particles could really pop out, exist, and basically this would affect the form of the RG equations and also the shape of this effective potential. But if we assume that, the store doesn't change really much, basically you will find a negative true vacuum at high energy scales, and these scales can be above the inflationary scale. Of course, you really need a UV completion to really have access to the precise shape of the potential here. Now, again, if we assume that we are in this kind of setup where the true vacuum in our world is negative, basically, again, one has to argue why, you can start high in the hilltop. It seems to be, very improbable, and yeah, one has to explain basically the initial conditions for inflation again. Now, as we showed in our more recent work, basically in this Higgs inflation model, we do have some Euclidean AdS wine glass wormhole solutions, and basically we can sort of realize our proposal that basically you tunnel up high up in the potential using basically the solutions, and then you follow this slow roll trajectory. And again, you need some kind of magnetic fields or actions. So is this clear?
Panos, what was the exact matter that you're considering here apart from the Higgs?
Higgs, and then, standard model basically. And we assume that in the early universe, you have some dominant magnetic radiation. Or, okay, we have to extend the standard model with some kind of axionic fields.
I see. Okay.
So these two options can realize our proposal. And okay, let me give you slightly more details. Again, you start from...
Hello?
Yes.
One second. So the fact that, so you run the Higgs potential, through all the thresholds, including neutrinos and all that, is that what you do? I mean...
Yes, so without gravity, this has actually been done in some papers. So this is known, even with all the standard model particles. But again, as I said, this assumes that there is some kind of desert in the UV, right? Because you don't know if additional particles above a scale are found, basically this would also affect the RG equations.
No, I'm just trying to understand. See, there's one thing to say what happens with just top quark loops, okay, and or heavy quark loops. It's another thing to say that what happens, how the Higgs potential gets corrected, let's say due to QCD, right? That we don't really know, I would argue, in the sense that there's a non-perturbative physics when you come down in energies. Shouldn't you know all that physics to kind of extrapolate it?
Well, these physics are more important about our, close to our vacuum, right? They're not really important for these high energy scales. In the high energy scales, I'm more, more worried about effects that would come, from new particles, and not from QCD effects at low energy, right? It's asymptotically free.
But cosmology is at very long distances, right? Shouldn't you calculate some?
Well, inflation is already at very high energy scales, right? Our current cosmology is here.
Okay.
For that, it's very important. For what you say, all these effects are very important for that. But here, for the shape here, I don't know. I don't think so. But there are other things that are very important, right? And we don't know. We assume that these things will not change the story principally. Of course, we don't know. That's an assumption. You might argue, okay, of course, from string theory that, string theory prefers to have, negative CC vacua. So from string theory, basically, most probably the true vacuum of the world, the UV is some, the lowest energy state in the potential is basically some kind of energy, negative energy state. But yeah.
The question I'm asking is that, this metastability at very high energies, how does it translate to any cosmological conclusion? That's what I'm not understanding. Yeah, because there's a lot of physics which happens in between.
Oh, that's true. There's a lot of physics that happens in between, let's say, in these scales, right? Your worry, I guess, is in these scales, maybe somewhere here. Yeah. Yeah, in our model, we haven't studied, let's say, fluctuations, as Subrat would ask before. There are many things to be done there. The only thing that we did is basically we assumed that, something that is consistent with some kind of evidence that we have, that basically some loop-corrected effective potential for the Higgs would take this kind of shape. And at low energy, we have some sort of control based on computations that other people have done. And okay, we extrapolate at high energies based on some kind of educated guessing, but that's a guessing. I completely agree. That's an assumption.
Okay.
Yeah. Okay, so if we assume all these things, that of course these are assumptions, basically you can show that these types of wormholes, basically you can use them to sort of go from this AdS minimum, basically high in the Lorentzian potential, but low in the Euclidean potential. And then basically you can follow the slow roll trajectory. And then, okay, in the context of Higgs inflation, this model is consistent with these constraints of inflation. Again, because, near this region, we assume that, okay, the results are close to being the ones of tree level. Now, of course, to realize our proposal, you need some magnetic radiation or actions in the early universe. We give some precise numbers for their densities, but inflation is basically the great diluter, right? Everything really dilutes a lot. And yeah, there's no observation, let's say, significance of these things to late times. So yeah. Okay. So this concludes, let's say, this more phenomenological model. So let us now go to some questions, interesting questions that were asked. So some comments and future directions. So as a summary, we proposed a new type of wave function for the universe computed from the gravitational path integral with asymptotical Euclidean AdS boundary conditions. And in the semiclassical limit, this describes the Euclidean AdS half wormhole. And if the scale factor has a local maximum, as we said, we can slice it and glue to it some expanding cosmology. Then we realize this with a non-trivial scalar potential and in a model of the standard model plus GR when phi is the Higgs. And this proposal basically evades some of the issues of the no-boundary proposal. We have well-defined probabilities because basically we have this AdS asymptotics. And of course, as was asked also by Loga and I guess Subrat, it would be very interesting if it is possible to really describe this physics of inflated cosmologies and perturbations within the context of holography. And this would basically entail understanding whether there are microscopic duals of Euclidean AdS wormholes, or these appear only by doing some kind of averaging, as other authors have argued. And let me now go to this slide related to embedding, and here you can ask me more questions. As we said, the big question is the following. Are there microscopic UV complete models of Euclidean wormholes in AdS-FT? And by this, I mean actual string theory on a target space wormhole background. So the two-dimensional solutions are not good enough because you can always say that, okay, I have some kind of UV-like theory, and this is actually a worldsheet, not the target space. So you actually need, some kind of real string theory on some target space wormhole background. So this question, of course, is closely related to the original form of the factorization problem. And there are two solutions. Either these wormholes appear only by doing some kind of averaging, statistical averaging, or there could be some kind of interactions. Basically, you have copies of CFTs interacting in a strange way, and then this gives rise to some kind of wormhole in some more controlled way. So I don't know about this question. The jury is still out. So did this slide, answered the question that was raised, or maybe there are more comments about that? I don't know.
I have a small question.
Yes.
Do you know if the kind of half wormholes you're considering can be thought of, like, for example, you have magnetic fields that are supporting your wormhole, right?
Yes.
Do you know if they can be thought of via these interaction pictures that you're saying here?
Okay, good. So I know such wormholes that. So the main problem is the following. So in the interacting picture, I don't know how to make wormholes where the throat has a local maximum. So all the wormholes that I know have a local minimum.
I see.
So I don't know what is the, it would be very interesting to really understand what is the field theory counterpart, even at bottom-up level. I'm not saying now something top-down, where the wormhole basically bounces and has a local maximum. I don't know what this really means from the field theory, how you can get that. Even from, from a purely bottom-up level.
Right. No, I don't even mean like the de Sitter part of it. Just consider the Euclidean AdS part of it, for example.
Yeah, it's
even in that case, we don't really have a microscopic like CFT understanding of these even axion wormholes.
Microscopic, no, but you can have some sort of, like a bottom-up idea what the correlators look like.
Yeah.
Stuff like that. But microscopic understanding, I totally agree. We don't know. And there are people that argue that the only way to get these wormholes is basically through averaging. So you have some kind of, so in the universe, this would mean the following. You have some kind of, let's say, chaotic dynamics in the early universe, and then this wormhole basically arises from that. Right? That would be the ideology.
I see.
But yeah, this we don't really know.
Yeah, thank you.
Okay, another thing that one might try to do is to do some kind of supergravity construction. So we are working on Sugra models. So there are indeed examples in a racetrack type of superpotentials that I draw here, such as the Kalos-Linde model, where basically the scalar potential looks like that. So these are good for our scenario. But usually people try, like in KKLT, they try to uplift the whole potential. If it's negative, they try to uplift everything in positive values. But for us, for our setup, it's actually more natural to uplift, let's say, part of it. Just uplift just a small region of the potential a bit. And okay, you don't need, a very, very strong uplift of the full potential range. Now, I know I have discussed with other people like Fernando Quevedo with emails, and they are working and they have found some similar, let's say, solutions. But actually, I don't know yet how to realize our scenario and at the same time get realistic, let's say, spectral data from supergravity models. So I can realize our scenario, for example, like in this Kalos-Linde model, but this, for example, has an S close to 0.4. And then, okay, this is not good for our real world. And again, okay, one might think, okay, maybe we could add some non-minimal couplings, etc. That's a possibility. But again, it would be interesting if we have some more clean string theoretic embedding. Sorry, maybe there's a question about this slide. I left very fast. Okay. And then the last comment is, I guess it was asked by Suvrat. It is also important to compute cosmological correlators in our setup here. So you can insert, let's say, some operators here in the vol and compute some correlation function at late times and basically compare and contrast this with the no boundary proposal. We are currently trying to study this. So far, I mean, these are not yet complete results. It seems that if you pick the Euclidean AdS vacuum, if you pick the vacuum here, basically, because the geometry here looks quite similar to that, you don't find some big deviations from the no boundary proposal, but okay, that's still something that needs to be worked out in more detail.
Can I ask a question here, actually? Can you examine the limit of this setup where your late time surface becomes exactly de Sitter, you're not in slow roll?
Where your late time surface, you mean here, becomes exactly. Yes. I guess so, yeah. Of course, this would involve some kind of very fine tuning of the potential such that, it becomes exactly flat at late times.
Yeah. So then, we had a complete classification of all solutions to Wheeler-DeWitt in asymptotically de Sitter. So then this state that you get, it's not only, by the way, no boundary, there are many other solutions. The state that you get must be one of the states that we had in the complete classification. And in this case, it would be surprising if the cosmological correlators were exactly the same. In fact, I think they cannot be exactly the same. The proof is that, you look at cosmological correlators in any small region, that's enough to completely identify the state. So that's this version of holography of information in de Sitter space. So if one could look at that, now that only works in the, our analysis was only in the exactly de Sitter limit. But if one could look at that limit, then it's clear there have to be some differences. Maybe not for 3-point functions, because that would be fixed by conformal invariance up to a number.
Exactly.
At the moment you go to higher point functions, you would get some differences. And it might be interesting to see also, how it fits into that framework.
Yeah, that's what I was going to say. You need higher point function.
Okay.
Yeah, that's an interesting direction. I agree completely.
Okay, thank you.
Thanks. Okay, and then we have some. I also have some other future directions. As I said, we need to run these RG equations for various scenarios to fix the shape of the effective Higgs potential. Assume, I don't know, some kind of SUSY, maybe, or various scenarios, and then check also these perturbations in each of these scenarios. We can check also, try to see if these magnetic fields that we assumed, or these actions, basically can survive this dilution. Maybe there are some kind of seeds for the galactic dynamo or some kind of nonlinear effects. We don't know this, and that would be interesting to study. Also, actions are interesting for beyond the standard model phenomenology, and people have argued that perhaps they can even explain some current observational data, like the ones that come from DESI, that show that dark energy seems to dilute. Then, as we said many times, it's nice to develop a holographic picture, at least from some toy model or bottom up. And yeah, it also would be interesting, as it was asked, whether you can actually realize some kind of quantum field theory or setup, and then to have some kind of properties that resemble our setup and the wormholes that we find, the computations that we find from these wormholes. And with that, I'd like to thank you very much for it.
Thank you, Panos, for the nice talk. Are there any questions or comments?
Yeah, I have one question, Panos. This is hi. Nice talk. Why is there some compelling reason you have to identify the Higgs with the inflaton?
No. It's not a compelling reason. It's just a possibility seems the only scalar observed particle, right? Because if you have the inflaton, there are some troubles. Sometimes you have this long-range fifth forces, and there are issues if you assume that there is an additional scalar particle that we haven't observed, right? There is some tension sometimes, but I totally agree. It's not the only possibility, of course. Yeah, it was just a simple context where we could, realize our setup. Yeah.
Thanks.
Are there any more questions? Okay, so if there are no further questions, then let's thank Panos again for the talk. Thank you so much.
Thank you, Panos. Thank you.
Thank you so much.
Nice talk. Thank you.
Thank you. Thanks.
All right.